Greetings all, my name is Elena Becerra and I will be presenting to you a hexagonal close-packed crystal structure. So what is a hexagonal crystal structure? It is a metallic crystal structure, also known as HCP, and has a unit cell in the form of a hexagon. Some common metals include, but are not limited to, magnesium, titanium, zinc, and cobalt, which is what this image on the right represents. To begin, the number of atoms per unit cell will be explained through a 3D model that I have created here on the left. This includes two base-centered atoms, which are these half spheres colored in green, one on the top and one on the bottom, as well as 6 corner atoms surrounding one of the half spheres that are 1/6 of a sphere. So there are 6 on the top as well as 6 on the bottom, which are 12 corners in total. There are also 3 mid-plane interior atoms, which are these red spheres here. This can further be represented in the 3D model I created through Tinkercad. So we'll focus on this image on the right. As you can see, the 2 half spheres here, followed by its 6 surrounding atoms and the 3 interior atoms. Also note that I did separate these and they are supposed to be touching each other. I just did this for the sake of a better visual representation of what's going on. So this further comes down to the amount of unit cells or atoms per unit cell, which is 6 once you plug it into this equation down here. Now for the volume of unit cell and geometry. So an HCP model does have a coordination number of 12. This is computed by, if you see this image on the right that I have created, if you look at this green centered atom here, you can see that its neighboring atoms, which are these blue spheres, there are 6 of them, followed by the 3 interior atoms, these red spheres, which are 3 more, and above this green centered atom, there would be 3 more red spheres. So this comes down to a total of a coordination number of 12. 6 blue ones and 6 red ones in total. Now, for the volume of this unit cell, can be computed by the area of the hexagon times the height of the prism. So this can be further reduced down to 24 times the square root of 2 times the radius cubed. Now, for the stacking sequence. As you can see from this image on the right, it does have an AB stacking, which the blue spheres would be A, the red spheres would be B, and the blue spheres again would be A. Now this green sphere in the middle is just to present the center atom, so it should be blue as well, if you want to think of it as the AB stacking. This further introduces the atomic packing factor of this crystal structure. So the atomic packing factor can be computed by the volume of atoms per volume of unit cell. Now, from the previous calculations, this can be reduced down to pi over 3 times the square root of 2, which comes out to be about 74%. Now, as well as the 3D model I created, I did have a visual representation of that as well. As you can see, these are tightly packed, with the blue spheres being A again, red being B, and blue again being A. As you can see from the top, you can see the void fraction a little better. So these are supposed to be a little bit closely packed, but as you can see, the 74% of void fraction in this. again, so this also means that the 74% atomic packing factor indicates that the efficiency of the packing is very, very well for equal size atoms. And these are now my references. And I will now leave the floor open for any questions. I hope you enjoyed this video and you have gotten a better representation or understanding of an HCB crystal structure characteristics.